Oh, hi, everybody. Welcome back to the VM Workshop in 2021. Our next speaker is Monte Bauman, a friend of the VM Workshop for a while, and he's here to talk to us about some hardware things. So Monte, over to you.
Thank you, Bill, and hello, ZVM Workshop, one of my favorite gatherings of people, and I'm so disappointed we're not at The Ohio State University this year, which is my hometown and my alma mater, but nonetheless, happy to participate, and I'll be talking in this session about the Z15 chip, and this is a hardware story about how and why this chip is awesome, and how and why it makes the Z15, how and why it makes the Z15 special, but how and why it makes the LinuxONE 3 server special, in particular, in context of this workshop. So the abstract will be in the materials that you can download and read, but the short story is, all chip producers have been challenged by the maintenance of Moore's law, by the continuance of the concepts related to Moore's law, but challenged in terms of physics. So we'll talk about that a bit, and we'll talk about how the Z chip has done a pretty darn good job maintaining the concepts of Moore's law under the duress of those physics. My introduction is alluded to here. I've been in the mainframe space for quite some time. I started my career in Endicott in the early 80s, working in the Glendale lab, helping to develop small mainframes, the 9300s, the 4300s, and the like. Then I moved to the field, became a systems engineer, and have been essentially a systems engineer ever since. So part of that means I get to explain technology to our clients, and this storyboard is one of the funner ones I get to do from time to time when a client has a deep need or curiosity or interest in the technology. So I get to tell this story, and why is it moving by itself? So I'll be repeating that story here, and really just kind of walking through how a machine is built, and starting with the core. So core starts with a blank slate that the engineers are going to create pile of transistors to implement a machine architecture. In this case, an IBM Z architecture. It starts with the registers, the instruction pointer, and the notion that there's going to be a pipeline that's going to run at a certain frequency, as fast a frequency as possible. So we built a pipeline designed around that 5.2 gigahertz clock speed, which is really, really fast. The other aspect of why this core is cool is this out-of-order execution idea. It's the idea that the pipeline can execute instructions in an order different than they are received, different than they are coded by a programmer, for instance. And we'll see why that is on this chart, and that is there's many execution units available to the pipeline, many places to park the instructions, to dispatch the instructions is probably a better way to put it. And so if we've got instructions organized in a way to optimize that multiple execution, and sometimes that's called superscalar, it's a great thing. And we'll talk about that more in a second. The other great aspect of design in this machine is the L1 cache and the L2 cache, and really just the caching of instructions, the caching of data, and the caching, as we'll see soon, of history and branches, and caching of address translations. We cache a great many things to keep that pipeline from stopping. So all machines wait at the same rate. If the pipeline stops, then we're all in trouble until the pipeline starts back up again, until something's cached in and the execution can begin again. So large investment in cache, and not only investment in sizes of cache, but very sophisticated caches. Caching of address translations is as mentioned. So there's a translation look-aside buffer. Each and every virtual address translation is cached and remembered, and helps us keep that pipeline running. The superscalar nature is alluded to now in this graphic. Multiple load store units, which is to say we can execute 2 load store units instructions at the same time. 4 fixed point units are available. And it might be no surprise that the bulk of the instruction set is fixed point units. That's the most important, most popular, most prevalent instruction type use. So there's 4 units for those purposes. They can be dispatched simultaneously. Branch units. Well, branches are pretty important to a programming model, a programming language, and they're pretty prevalent as well. So we've got multiple places where branches can be executed, and we'll see soon a branch history table that is in support of the branch unit. And that branch history table helps us do things like branch prediction. And branch prediction is really the notion that we want to influence what stays in cache. We want to influence cache to retain instructions that we may well likely come back to. So that if we do loop and we do come back to those instructions, they're there and we don't have to page them in and look for them in the L2 or in other cache units. So it's a unique attribute of this instruction set, and a lot of attention placed in the branch area. But modern applications are important to keep happy too. So a lot of advanced math, a lot of character manipulation are done in what we call the single instruction multiple data unit. And that's basically a vector unit. So we can do vector math, we can do vector arithmetic, we can do vector, and all the way look at a vector is it's a character string. So we can do character manipulations and character based operations in the SIMD unit. And the Java compiler happens to do a ton of that. The Java compiler happens to do a ton of stuff in floating point, a ton of stuff in character manipulation. So the attention we've placed in the SIMD unit has really helped with Java operations, Java performance, as an example. And then at the bottom of this is the compression and execution, compression and encryption unit. So this is kind of, 3 or 4 generations of processor ago, of chip ago, so to speak, we started paying a lot of attention to the security space and doing in hardware what's hard to do in software. So examples are encryption and decryption. Examples are compression and decompression. And in this chip, examples are sort. And so we've implemented in hardware, and you'll see this pattern continue into the future. We try to very much to implement in hardware those hard to do things in software. And it's been a great success, actually. So the CPAC-F facility, the encryption, decryption capabilities that are instituted into the chip have been a great win. And the compression, and we've been doing compression since the 90s, but we keep adding compression algorithms. We now can do Love-Zempo, we can do Huffman, we can do a great deal better compression support for the hardware we've implemented. Now, the normal core runs in SMT1 mode, which is one set of registers, one instruction pointer, and that pipeline really has one instruction stream to worry about. But in the Linux space, we like to run in SMT2 mode, where that pipeline is not just running a single instruction pointer and a single set of instructions, but 2. So that is what we call SMT2, simultaneous multi-threading with 2 threads. And now you can see, and you can kind of get the sense that those many execution units can be much more productively utilized for that pipeline dispatching 2 sets of instructions. So we can get, sometimes half again more throughput out of this core for running in SMT2 mode versus running in SMT1 mode. So hopes be that and mileage can vary. So based upon caching patterns and the like, you can hit the knee of the curve at different resources within the core. But generally speaking, SMT2 mode will give a throughput advantage over SMT1 mode of 25%, 30% or so. And we've spent a lot of investment in the improvements SMT2. So generation 1 SMT2, generation 2 SMT2, and now with this chip, generation 3 SMT2 is that much better. The other part of the pipeline story and the core story is the new instructions. So every machine has added more instructions, different instructions, some driven by the compiler folks. If they could just do something a little bit differently, they could compile in real time in a JIT, or they could compile in a static compiler. They could compile better machine code. So a lot of instructions have been added for that very purpose, and a lot of benefit has been yielded in Java performance as in particular, but not to forget that COBOL performance and PL1 performance, they inherit these changes as well, just in static form. So the instruction set alive and well and very vibrant. Now, performance is the gist of this talk, but can't forget that this is an enterprise serving server, so RAS is important. So there's a couple comments here, whether it's dynamic core sparing, first failure data capture, the server can phone home. These are things that we take for granted sometimes in the LinuxONE or mainframe space. But those capabilities are core and very important, and they basically start at the core level and then build up through the system. So as a core, hopefully this is illustrated that there is just a lot of cool aspects in each and every core: workloads, acceleration, superscalar execution, a lot of investment to prevent pipeline stalls, caching. And then when you look at the chip then, which is built out of these many cores, I could argue that there's 9 billion reasons to like this chip, which is to say there's 9 billion transistors on the chip. And those transistors are allocated across the functions performed by the chip, and which is in part the cores. So there's 12 cores on every chip and another great big pile of cache on the chip. The level 3 cache is shared across all those cores. And the final thing on this chip is another kind of shared execution facility. That's the asynchronous data mover. It's the gzip compression capability. Used to be you had to buy a compression card, put in the IO cage, and we've miniaturized it and built that capability, that function, into each and every chip at this point. So the miniaturization continues, the stacking of capability continues. So the chip, hopefully you can see, is a great chip. There's RAS built into that chip. There's function, performance, density, and we'll kind of see some metrics here shortly related to the progress of this chip compared to the chips that preceded it. Now, chips are what's used to build out the drawers. So as we continue to look at how we construct a LinuxONE server, you see the processor drawer, and you might call that the motherboard. A lot of folks might think of it as a motherboard. And what's on the motherboard, what's on the processor drawer? Well, there's sockets, there's places to put chips. But there's also another, surprise, big level of cache, another big set of sophisticated cache on the storage control chip. The storage control chip supplies cache as well as interconnects to other processor drawers. And what else is on the processor drawer? Well, there's the DIMMs, the memory chips themselves. And the final thing on the processor drawer are fan outs. If there's other processor drawers, there's connections to those drawers. There's certainly going to be IO drawers in the system. There could be coupling facility links and the like. So there's fan outs from the motherboard to other aspects of the server. So it's quite a dense fabrication of capabilities, chips and cores, and we can take that drawer and now we can build systems out of it. So in the LinuxONE LT1 server, the first single drawer system is called a MAX34, and MAX34 almost makes sense when you think of it this way. There's a single drawer and it provides a maximum of 34 cores that can be characterized. It also gives you a maximum of 8 terabytes. In the LT1 line, you can get multi-processor drawer configurations. A 2-drawer system is a MAX71. It's a 3-drawer system's a MAX108. A 4-drawer system's a MAX1045. And the top of the line, MAX190, is a 5-drawer system. So you can have up to 190 cores, 100 and up to 40 terabytes of RAM on that system, and up to, if you recall your MIPS parlance, it's 200,000 MIPS, which is kind of remarkable. I remember when I first started the business, a big system was about 65 MIPS. So now we're putting 200,000 MIPS into a single footprint, So in summary, you can see how this is quite a scalable product line. Start small, you can grow and grow and grow to a fully connected fabric. The LT2 is the secondary server, the mid-market server. Uses the same motherboard. It's just constructed a little bit differently. Runs in a totally air-cooled fashion, as opposed to LT1, which has radiator and runs at the 5.2 gigahertz. This guy runs at 4.5 gigahertz because it's air-cooled. It's a single frame system, so it's got a one socket max 04, a two socket max 13, a three socket max 21, a four socket max 31, or its largest iteration is an 8 socket max 65, and the max 65 is two fully populated drawers, as alluded to in the drawing here. So when you look at the server and how to build it out, you can see that for example, an LT1 could be built out in a rack, a single rack. Here we see the radiators at the bottom. You see a processor drawer, and you can reserve space for future processor drawers if you're going to grow or suspect the need to grow. But you're going to put an I/O drawer in there as well somewhere. So you got to connect Ficon cards or fiber channel cards to NIC cards, OSA cards to the fabric of your I/O connectivity. But we've kind of built this scalable notion of the system, so you can grow from a single drawer to a second drawer. You can grow from that first rack to a second rack. And that's all non-disruptive. You can add the third I/O drawer. You can add another processor drawer. All of this is remarkably non-disruptively capable of expanding your system as you grow forward. I think the only disruption here in this illustration is when you add a processor drawer, you do have to, I believe, you have to stop and start your system. Actually, no, I think with concurrent drawer repair, you're good to go. So it's a remarkably resilient and scalable system from a non-disruptive growth perspective. The last, a segue into the logical piece of this is kind of this idea that we've got a computer science equation. I like this equation. Hopefully you like a little bit of math. So what makes for a fast thread, a fast core? What makes for performance in a core? Well, it's an instruction set that's very capable. It's a big and smart cache that reduces memory instructions that have to be executed in firmware. But it's also superscalar, as illustrated before. We want to execute as many instructions per cycle as possible, but at a clock speed that's very fast. So if you use this equation, you can see that the units cancel, and you come up with the minimum number of CPU time per second in seconds per workload is a great and wonderful thing. And if you look at the system a little bit wider and look at the server from a throughput perspective, then you take that fast thread and then you insert I/O capability, insert the ability to reduce synchronous wait on I/O, reduce dispatchable wait time, waiting for dispatchable engines. So these two equations kind of allude to fast core performance and fast server performance. If you look at the first one, these are all the features we just talked about. What is it that makes for a fast thread? We talked about branch prediction and smart caches and large caches and things that keep minimize the memory instructions that need to be executed for a workload. We also talked about the number in the programming model, the sophisticated complex instruction set, the new instructions, be they packed decimal, modular arithmetic, SIMD instructions, the CPACF instructions, the workload and acceleration instruction. All those capabilities reduce the number of programming instructions needed per workload. Then cycles per instruction, that's the superscalar, that's the out of order execution. That's the notion that we can execute up to 12 instructions per cycle when we can take things perfectly out of order and dispatch them across the superscalar nature of the machine. And then finally, you get to the fast clock speed. So it takes a lot to make a machine fast. And what we'll see soon is we've been to 5.2 gigahertz before. But in each iteration of the chip, we get better at all of these other things. It's one thing to run fast. It's another thing to prevent pipeline stalls. It's another thing to reduce the instructions per workload. So engineering is very important from a systemic perspective if we're going to achieve, Moore's laws, concepts or precepts. And then from a workload perspective, fastest server perspective, it's one thing, and it's a great thing to have a fast thread, but it's an even better thing to have the best throughput in the world out of your server, and that comes from reducing synchronous I/O wait, and you do that with a large number of capabilities, whether it's compression to reduce I/Os, whether it's shared memory communications to reduce network I/O times. And then there's a lot of ZOS features in here too. And it's as simple too as 32 gigabyte per second fiber channel protocol or 35 gig NICs. So the ability to reduce I/O wait and synchronous wait is great. And then the ability to reduce dispatchable wait time is great too. SMT2 does a lot of that. Having just large SMPs and lots of CPs and IFLs available is a great thing. So this server, is engineered, basically soup to nuts to offer fast threads and high throughput servers. We know that because we do benchmarking. The benchmarking we do is usually in terms of MIPS, which has lots of meanings in the industry. Some of them are more fun than others, but basically a unit of capacity is useful to have to compare one chip versus another chip and watch the progress of capabilities. And luckily LSPR is a benchmark that hardens the generation of those numbers, and it's a terrific piece of work that's done year on year, product on product, chip by chip by chip. It gives us a nice historical and accurate rendition of the capabilities of these cores, the capabilities of these chips, and the capability of these systems. And we can see through history, by looking at MIPS and get a pretty good idea how things evolve. Now, this is not an IBM chart. This is a MIPS story from Gartner and other sources, but it kind of indicates and gives you a kind of a perspective since 1994 when we went to CMOS. If you remember the 9672 is a generation one, we started CMOS and we had a 15 MIP core, and then you bring that clear down through history through the 2019 where we've got the Z15 chip, and we've got a core that's something like 2,232 MIPS per core. But don't look at it just per core. Don't look at it just in terms of the third column. Look at it too in terms of that fourth column, the MIPS per chip, which is really what Moore's law is about. It's a chip statement, not a core statement, a chip statement. How much work can you get out of a chip? And so you look at that first chip in 94 where we got 15 MIPS per chip because it was a single core. A core and a chip were the same thing back in that day. But now you fast forward to 2019 and you look at a Z15 chip, which is a 12 core chip, and you get 23,000 MIPS out of the chip. So from 94 we were 15, and 2019 we're 23,000. Then, and of course, you can look at a motherboard, which is the fifth column. You can also look at the sixth column, which is single system image MIP. Basically, look at it from a server perspective, which is a fun one too, because we started with about 61 MIPS in 1994 out of a G1 CMOS-based server, and then we get to in 2019, a 240,000 MIP capable server. So pretty, it's kind of fun to look at the historical perspectives. And again, this is kind of that notion that you look at LSPR data, you can look at it from a couple perspectives. You can look at it from a core perspective, from a chip perspective, from a motherboard perspective, and from a KEC or server perspective. And if you look at the bottom of this chart, you kind of see how cores have evolved over time. See how chips have evolved. And this is really the last 9 generations of servers since we went to a high-speed pipeline So the Z10 really got us started on high-speed pipeline, but the Z900 was kind of the first iteration of the kind of the modern CMOS generations. So and that's really too where how far back I could go with LSPR data. So I went back as far as I could with the LSPR that's available today, and this kind of gives us that perspective of fine granular detail of data, and it gives us the ability to do some comparisons from a hardware perspective. And this is a fun one. It shows how we have so many more MIPS per core, so many more, and this one's particularly interesting in this day and age. How much energy are we consuming? And this shows that from just basically 10 years of progress, we're 700% better at executing instructions per watt than we had been. So we could do 1,500 and change MIPS per kilowatt on the Z10, and now it's 10,000 MIPS per kilowatt of energy out of the system. So just remarkable changes in the technology, remarkable additions to infrastructure. And here's just the charts. So if you wonder how we are doing in terms of MIPS and Moore's law, these charts kind of map that out. Moore's law is this red line, and you can see how the MIPS per CMOS PU chip is the blue line. And we were doing great until 2015, and then Moore's law started taking off when we look at it from a chip perspective. When we look at it from a platform perspective, we were right on target from a platform viewpoint. The Z15 came out just in the 2019 timeframe, and Moore's law was suggesting we'd be right there at that 250,000 point, and that's where we were. So it's kind of interesting to look at the numbers again from a historical perspective to see where we are. So just to wrap up the Z hardware story, as impressive as some of the benchmarks we've done and been doing. If you're running a workload and looking to see whether this machine would be viable, there's a series of proof points that might be similar to work that you're running. This is kind of a smattering or a collection of some of those proof points. But it's illustrative of some of the comparison points we have with the distributed servers and the Z servers, the LinuxONE servers. And then in general, the Z chip is awesome, but the LinuxONE servers are built out of those Z chips. So we think LinuxONE servers are terrific. They offer favorable economic outcomes. They offer operational excellence. They offer mitigated risk. And it all starts with that core, with the resilience built in, the performance, the ability to run much more work on many fewer cores, drive down software costs that are related to cores, and drive up operational excellence for the flexibility, the performance, and throughput that server is built to provide. So that's pretty much as fast as I'm able to do that presentation. Hopefully it wasn't too fast that it didn't make sense. Trying real hard, Bill, to keep on schedule for you and your team. So hopefully that was a decent job of doing that. So I'm able to take questions and or dig into any other information and or show you a spreadsheet if it helps where these materials have been tracked and generated. So I'm at your service for the next couple of minutes. How can I be of help?
So there was a question in the chat. The question was, will there be a time when more than 2 threads make sense?
Yeah, that's an interesting question. I've heard that question asked before. Basically, we asked that question a lot right after we introduced SMT2, knowing that the Power brand was doing SMT2 and SMT4, and Power can even go to SMT8 for certain configurations. So we wondered if the Z core would go to SMT4 or anything different than that. So we asked that question of the engineers, and the reply we got back was SMT2, and because of the design point of the Z chip being more of a performance per thread, a thread performance oriented chip design, that SMT2 was kind of the natural design point, and they basically, in a nutshell, said that no, SMT4 was not going to be in the future. We were going to get performance and throughput through SMT2 and through multi-core chips versus through smaller core mappings to chips and larger SMT factors. So it was their considered opinion, and you can kind of see the trade-offs too in the power brand as you ask your pipeline to do more coordination, and that's what SMT2 drives, is coordination through the pipeline. You actually make that pipeline run slower because it has to do more coordination. So if we want to stay with a pipeline that's in the 5 gigahertz range, we have to keep it simple enough to stay that fast. And SMT2 is kind of that balance point between a very fast clock speed and a sophisticated pipeline, but not one that's burdened too much such that it has to go slower. So hopefully that makes sense. That's the story I've heard. Can you comment on the importance of the 2 nanometer versus 14 nanometer size? Yeah, I've read that story and saw how IBM came out with KIT and proof of concept around 2 nanometer, and it is important. And basically, it's there's a couple important things coming down the pipeline that are going to help us systemically achieve CMOS, achieve Moore's law-like capabilities. We're not going to get it right from the cores, right from the silicon. Not all of it, but the lithography capabilities of shrinking the circuitry more and more is going to give us some of it. So 14 nanometer is pretty common today. It'll probably go to 7, in the not too distant future, and then eventually to 2. But it's kind of an exponential thing. Each time you get a little bit smaller, the cost of plants needed and the equipment needed to do that just goes up and up and up. So CMOS has it's decade, probably a decade or so, but an end of life in the sense of the physics just catching up to us. So we have to do things differently. We have to think differently. We have to think of vertical structures, 3D chips rather than 2D chips, and the like, stacking memory on top of chips, just kind of doing away with motherboards and creating systems out of semiconductors that are grown vertically versus connected across a planar board. So there's a number of things afoot. 2 nanometers is certainly a very, very important one, but these other packaging and connectivity and using light rather than electricity to connect chips and to connect distant circuits, there's a lot of stuff that the engineers at IBM and other companies I've read about a bit about, and they're doing. So the future, even though we're not going to achieve Moore's law in the typical way, the future is still very bright in that we're going to continue to achieve and in some ways overachieve Moore's law in new and innovative ways. So hopefully that answers that question a bit, even if I'm waving my arms in the doing. Any other questions in the chat, or any other questions that want to come online?
So Monty, I had a question.
Yes.
Am I allowed to ask questions?
Yes, you are, Bill. As long as it's a softie, go ahead.
So I know with your role, you get to talk to a lot of different people, a lot of different clients, and also talking to ones that are new to the platform. So I know you covered a lot of things today, but is there something that we do on IBM Z and LinuxONE that is most surprising to folks that aren't familiar with it? Like, is there something that jumps out that we kind of take for granted? I mean, you covered a bunch, but I'm just looking for something that is more of a shock factor to the other folks.
It's probably the attention. It's probably the idea that this server is engineered so heavily, which is to say, we engineer into LinuxONE a great many capabilities. If you want, 24 NIC cards, that's okay. If you want, 36 FBA cards, that's okay. If you want, 190 cores, that's okay. The amount of engineering we do into the system is just phenomenal. It helps explain why there's a pretty good price tag associated with it. You pay for that engineering. So as you talk to a distributed server person, and if they give you the time and they're good, curious people, and most of them are, and you dig into the engineering that's done under the covers, they quickly come to the realization that there's a terrific engineering done inside the server, which is to contrast with their world where they in the x86 space have to do a lot of engineering on top of the server. So they've got the pizza boxes, they rack them, they stack them. And then to get resilience, to get connectivity, to get integration, to reduce latency, they've got to do a lot of engineering themselves on top of the server, or with in the fabric that connects their servers, or in the software and integration layers that connect the software on their servers. So it's you get to the same ends in quite different ways. And usually if one of the funner parts of this job when you get the time to talk to the distributed folks is taking them through the hardware story that we just went through, and to some extent, and then you layer that with the virtualization story, and just how we don't have just a single hypervisor. We've got the firmware prism layer, but then we've got and can have as much fun as we want at the second level hypervisor layer. Let's throw some ZVM at them. Let's throw some KVM at them. Let's throw some secure service containers at them, and build out really interesting virtualization structures on top of this really interesting hardware structure, and you basically build a centralized distributed server, or a distributed centralized server. I don't care which order they go in. And again, you get to kind of the same end of game, but in very different ways. And it's usually, the eyes light up and they start to get it as soon as we get through the hardware story and the virtualization story. And it just blows their mind that we can have, how many HBAs can you put on this box? Well, as many as you want. It's more than 2, more than 4. Wow. So could you comment on the quad TLB? So that was so when we first came out with SMT2, what was that? The Z13 chip, I'm guessing. But we found we kind of found, it's normal engineering, right? You find bottlenecks in design, and the bottleneck we found in the SMT2 implementation of the Z13 was the TLB. It was a single-threaded TLB, the translation look-aside buffer. Only had one execution engine in it. So it wasn't, so we found that was a bottleneck in going to SMT2. So when we came out with the Z14 and Z15 chips, they went to this quad TLB. So there are actually 4 execution units that do translations, and then they store the results into the same translation look-aside buffer, but there's now multiple execution elements doing translations. And so now when we go to SMT2, there's lots of places to simultaneously execute translations, and we freed up and got better performance, better throughput, better results out of the superscalar nature of the machine in SMT2 mode, and in other modes, and in SMT2.1 mode as well. So hopefully that answers that. And I think that was Phil. Any other hardware-ish questions I might be able to help with? That was a good question. Any other questions, Bill? I should ask you, Bill, if I answered the first question you asked me.
Yes, you did. I run into that kind of stuff too. I know, like the other thing that came up at one point was I had been talking about processor families, a new one, and talked about all the instructions we added. And I got this pushback because they didn't think that was possible. Because on other platforms, that's not necessarily the norm to add, dozens of new instructions in just a turn of the processor architecture.
Yeah, I was keeping track of the number of instructions per chip that we added, and it depended upon how you count them, of course. There's subtleties, but you know, it could be argued we've added, you know, several hundred, you know, over 700 new instructions to our instruction set over the last 5 or 6 chips. So just, you know, a lot of investment in architecture and instructions, and if you want to, under the covers of that big number is the SIMD unit. So we added SIMD. There's just tons of variations on the instructions in the SIMD math library. So hundreds of instruction variants came out of the SIMD unit when we added that to the chip. But you know, the transactional memory is kind of a fun one. When transactional memory came out, it came out first in the Z chip. It was the first chip, and anywhere, Intel, Power, ARM, anywhere, it was the first chip in the world to have transactional memory capabilities and the transactional memory instruction support. And that was kind of a remarkable thing. When was the last time, you know, Z was the first and anything? We tend to be that hardened, you know, we want to do things once it's been proven elsewhere to work. We're the risk averse technology stack. But every once in a while we go leading edge, and I think we're going to see some of that in the next chip, which I'm looking forward to talking about as soon as we get that guy turned around and out into the real world. So
cool. Thanks, Monty.
I know hardware is not always it's always a fun thing to talk about. It's not usually the first thing you need to work on. You know, software has to run somewhere. So let's think about really cool hardware like the Z chip. So that's my story, and I'm sticking to it.
All right. Well, it was, as you would say, awesome. So thank you.